Hello and welcome to lecture number 2 in this series on atomic absorption spectroscopy and ICP-OES. So at the end of this, we'll hopefully be able to do these things where we look at the hollow cathode lamp, we'll understand flame AAS, we'll look at the different comparisons of flame compositions, look at how choosing the stoichiometry there can change things. We'll talk about heating programs for the graphite furnace. We'll also explain ICP plasma. And we'll also look at radial versus axial viewing. We'll look at some background corrections, and we'll look at how we can perform external standard addition, and internal standard calibration calculations. So we'll go through all of these 8 topics today. So the hollow cathode lamp, its construction and principle. So basically, it's a little light bulb which has a cathode, which is made of an analyte metal inside, which is producing the light which is used to excite the element of choice from the ground to the excited state. So why do we need this special source? So a broadband source such as tungsten or deuterium cannot provide adequate sensitivity. Only a tiny fraction of photons coincides with narrow analyte absorption profile. We need a source that emits exactly the element's resonance line with a width narrower than the flame absorption profile. And so this hollow cathode lamp becomes our solution. So its operating principle is that it's filled with neon or argon gas, and these are accelerated to the cathode, and they sputter the analyte atoms in the gas phase. And so this causes, this is excited by collisions, they emit their characteristic spectrum, and then they return to the cathode. Okay, so the analyte metal cations are sputtered here at the cathode, then they go towards the anode, they hit the anode, and then this is where they produce that photon of light, which is element specific. So why is this HCl line with the determining factor in sensitivity? So if we look at the line profile physics, and the analyte absorption profile in the flame is broadened by Doppler broadening, i.e. atoms are moving towards or away from the source. Pressure broadening, which is our Lorentz broadening, which is caused by collisions with the flame gas, because of course, those are still molecules in the flame. Those didn't go away, they are a constituent part of the whole system. So these can cause broadening, and this broadening is significant. I mean, it doesn't seem like very much, 0.002 or 0.005 nanometers, but this is actually larger than the emission wavelength, okay? So any sort of, like, it's a doubling or tripling of the width of that line is significant, okay? And this results in a potential to change the fraction of the light which is absorbed and so on, because it's not falling exactly at that wavelength which is required. There are some alternatives, such as the electron discharge lamp, which is sometimes used for arsenic, helium, mercury, and thallium. So complete instrument then, so it has a system and a flow similar to most of what we've seen before. There's some sort of a light source, there is a sample container, there's a monochromator, there's a detector, but there's a few other things which are a little bit different. Like, for example, the chopper, which is a modulator. So this modulates the HCl beam, and so this is required in order to get a background and a signal, which can be used to produce a proper measurement. We also have the monochromator, which is of course required in order to isolate that single analyte line from all the other lines. And then we have a PMT, because oftentimes the individual photon events are not strong enough to actually be detected without the PMT. So we need this PMT to increase the signal significantly. So during this process, there is, of course, the need to burn the material. And so on the right-hand side, we see a schematic of the burning, where the best burning zone is the one in the middle. So the primary combustion zone at the bottom here is too cold to make sure that we have enough atoms. The secondary, we have a chance of too many ions. So the best zone is the interzonal, which is in the middle here, this yellow here. So how does the sample get to the flame? So first of all, there's a pneumatic nebulizer, which has a fast oxygen flow, which is what is sucking the solution containing our analyte up to the, up to the flame, all right? And so this moving very fast, and so it produces this relatively fast capillary reaction, which shatters the liquid into a polydispersed aerosol. Then we have a spray chamber where the large droplets are removed by baffles, and so only a fine mist reaches the flame. And so these large drops drain to the waste, which typically removes between 5 and 10% of the total amount of material. Then we've got pre-mixed laminar flow burners, so the fuel and oxygen are pre-mixed. We get a stable laminar flame, and so this is usually 10 centimeters long, which corresponds to that Beer-Lambert path length, okay? So different types of nebulizers and how do we choose them? So there are concentric or pneumatic nebulizers. These are the most common where the sample flows through an inner capillary. Fast oxygen flow creates the Venturi suction. And so this is pretty stable flow, small dead volume, pretty easy to clean. Although if you do have any dissolved solids, even a small quantity, it can result in clogging, which is of course problematic because it results in a variation in your flow to the flame. There's also a cross-flow nebulizer. So this is where the gas flow is perpendicular to the sample capillary. So this is less likely to block. And so we have a slightly lower efficiency, however. The V-groove or Babington nebulizer, the sample flows as a thin film over the groove and gas flows through a small hole in the groove wall, shatters the film. This is good for high viscosity samples. And then there's an ultrasonic nebulizer. So this is piezoelectric transducer, and this breaks up this high frequency breaks up the sample into a very fine aerosol. And so the efficiency is significantly higher than the pneumatic nebulizer. It does, however, require a desolvation chamber to remove the solvent vapor and improves the limit of detection significantly. But of course, it has a higher cost and requires careful maintenance, which is problematic. Okay, so you have a matrix for selection guide down here. So if the matrix is clean water, dilute acid, you can just use a simple pneumatic concentric nebulizer. But if you've got other things to consider like high total dissolved solids, or you have low limit of detection requirements, or you have high viscosities, which ones to choose. So then the flame types, how do we choose these for the correct chemistry? So air acetylene flame mixtures. So these are the most widely used. They're standard for routine atomic absorption spectroscopy, suitable for most of the periodic table, but not high refractory elements. So this is where we need our N2O acetylene mixture, which gets a higher temperature. So these are required for things like aluminum oxides, which are difficult to atomize in air acetylene mixtures. And so these are always used in, so we can choose actually our stoichiometry of our flames, whether we'll choose fuel lean, stoichiometric, or fuel rich. And this changes both the color and the temperature and the oxidizing or reducing nature of the flame. So if we have particularly low fuel, so that's a relatively low acetylene, more oxygen, more air, and we'll have an oxidizing environment, which is generally speaking not what we want because usually we're analyzing elements which are in the ionic form, cationic form. So like, for example, lead 2 plus or copper 1 or copper 2 or something like that, which in an oxidizing environment will prefer to stay as those ions. And so we usually prefer a reducing environment. So that's where we have a fuel-rich stoichiometry. So the graphite furnace, atomic absorption spectroscopy. So this has sensitivity beyond the flame atomic absorption spectroscopy. So there's a little oven, a bit like the one on the right-hand side here, where we can place the sample inside. And so because we're placing the sample inside before the measurement, we're actually avoiding the need for the capillary action that we saw and the nebulization that we saw in the flame spectroscopy. We can use tiny, tiny volumes of both liquids and solids for our measurements here. We have a much, much lower limit of detection, 100 to 1,000 times lower. So we're looking at nanograms per liter rather than micrograms. And so how it works is that this graphite furnace obviously conducts electricity. And so through resistive heating, we're able to generate high temperatures. And so this causes the hopefully complete atomization of the sample. And so this is the primary working bit for it. So during this, we have a 3-stage thermal program. So first of all, we have to heat the sample up to dry it to remove water or acid and things like that, because we don't want those damaging our measurement or reducing the sensitivity of our measurement. Then after that, we have the pyrolysis, which is the ashing. So this is a critical step because this removes any organic volatiles from this. The issue is, though, that sometimes we have very low boiling point elements in our metals, which actually will also pyrolyze or will atomize in this region, which makes it sometimes not the best choice to use this kind of technique for those measurements. Then after that, we have a rapid increase in temperature to try and atomize the analyte as quickly as possible, whilst also, of course, avoiding the interferences caused by ionization. So in this case, we're measuring the absorbance peak and we're looking to try and measure the peak area. So this GFAS can also be improved a little bit with the use of a Lvov platform. So the problem is that we often have, if we just put the ashes directly on the wall of the graphite tube, we heat the wall first, and then this heats the gas inside, okay? So its sample can dry and ashes directly on the graphite tube wall. And so the analyte atoms enter a cold, still heating gas phase. And so the matrix molecules and atoms are present simultaneously. And so we have more chemical interference and poorer reproducibility. So the gas phase temperature during atomization varies throughout the pulse. So we have non-isothermal conditions, okay? So what happens here is if we introduce what's called a Lvov platform, this reduces these problems. So the small graphite platform will rest inside the tube, but it's only contact with it at 2 points. So the platform is heated mainly by radiation from the hot tube wall and not by direct conduction. So it heats more slowly, okay? And the analyte on the platform atomizes after the tube wall is fully hot. And so the free atoms that enter a preheated stable gas phase at near constant temperature results in isothermal atomization. So the result is just better reproducibility, more accurate peak areas, and so on, okay? So typically, whenever we do this, we must change. I mean, it's usually preferred to use peak area versus peak height, but in this case, we really just have to use peak area, and it's due to its ability to be more accurate and to avoid small fluctuations in the atomization rate to give better precision and accuracy. As well as that, we can have problems with chemical modifiers in our GFAS. So the problem here is with volatile analytes. So some analytes, such as arsenic, selenium, lead, bismuth, and cadmium, are actually more volatile than their matrices. So this is a risk of like actually pyrolyzing and atomizing and ionizing and removing your analyte before we've actually even measured it here. So the solution is to add a chemical modifier and use something to bind the element of interest and prevent it from atomizing at low temperatures. So for example, you might want to use a palladium to alloy with volatile analytes, which will raise, of course, their atomization temperature. And sometimes the use of magnesium nitrate will produce an oxidizing micro environment for matrix removal. And we can also use ammonium hydrogen phosphate to stabilize lead and cadmium by producing stable phosphate compounds. And ascorbic acid can also be used to reduce arsenic to the less volatile arsenic atom or arsenic 3+. So calibration in atomic absorption spectroscopy. So there's three main strategies. There's, of course, external standard calibration, which is our commonly used form, which is just prepare 3 to 5. Realistically, you want 5 minimum different solutions, which will bracket your unknown. Producing a linear curve will remain within the limit of linearity and so on. The second one then is standard addition method, which we've covered extensively in module 1 and a little bit in module 2. So this is where we spike the analyte directly. This is whenever you have a complex matrix usually, where it's difficult to produce an identical matrix for standard and unknown. Then the third one is the internal standard method. So what we do here is we add a fixed amount of non-native reference element to all standards and samples. So we can normalize the ratio of the analyte to the internal standard. And so this corrects for any instrument drift, nebulization variation, and multiplicative matrix effect. So this is useful for ICP-OES or MS, but can also be applied to GFAS where there is significant drift. So here you want some sort of like, just a reference point whereby you know the amount of the reference material that you've added. And so that means that the peak area that represents that accurately represents the amount that you've added. Okay, so let's look at our worked example number 1 for the external standard calibration for copper by FAS. So copper standards and an industrial effluent sample were measured here. So we have blank and 5 unknowns, which would generally be our minimum, and then we have our unknown sample. So the first thing is to look at the calibration slope and the R squared. So the calibration slope is over here, so we know how to calculate that from module 1. So that's just going to be the absorbance times the concentration. So it's going to be the Y value versus the X value for each point, all over the squares of the CI. And so that means we get a M value, our gradient is 0.1603 AU per milligram per liter. And then an R squared value will pop out of that at 0.9999. Sample concentration then is given here. So the absorbance of the sample was 0.274. So all we over the gradient will give us a concentration of the unknown as 1.71 milligrams per liter. So we can then check this against the DENR compliances, and we find that it's 71% above the effluent limit. And so that is, of course, in excess. And so that means that the either a penalty would be enforced or that the processes would need to be stopped, and any containment measures would need to be reevaluated. Sample 2 then is the standard addition of lead in our wastewater. So the wastewater digester is 50 milliliter volumetric with an unknown amount of lead. And so 3 additions of 5 milligrams per liter of lead stock solution are shown below. So this is for a standard addition method. Again, we can calculate our slope through linear regression. We can get excellent linearity from that. Then we calculate the intercept as being 0.312. So this is a signal from the unknown alone. And so then we can extrapolate A is equal to 0. So this is going to be 0 is equal to 0.1247, which is our gradient, times the concentration, which is what we have to know, plus 0.312. And so we find out that the concentration added is given there. And so the concentration of our unknown is going to be 2.50 milligrams per liter. So we look at the DN, our surface limit, is 0.05 milligrams per liter. And we see that this is far in excess of what is allowed, okay? So why ICP-OES? Why do we use ICP-OES? So the limits of atomic absorption spectroscopy can be overcome. So remember that one of the critical limitations of atomic absorption spectroscopy is that we can only measure one element at a time. And so we had a problem in the last one with our nickel laterite mine thought exercise, that we needed to analyze 9 elements with 150 samples per day. And so this was just unfeasible using a fast instrument. So we needed to switch over to the ICP-OES. And so this would reduce both our limit of detection, make it much more suitable, reduce the time delay. So for example, GFAS is very, very slow. I mean, whilst its limit of detection is much lower than flame atomic absorption spectroscopy, it is also a lot slower because you've got the heating lag and things like that. You also the cleaning parts, which is much longer than doing it for a flame. Then the flame fails to obviously to atomize refractory oxides because it can only really reach about 2,900 Kelvin, and its linear range is quite small as well. The ICP-OES advantage is that there's a simultaneous 70 plus elements in a single run. Plasma is very high temperature and can ensure complete atomization. We have a massive linear range from nanograms up to grams. We have a high throughput, so we can get hundreds of samples per day for multi-element panels, and we have an emission mode, so plasma is the source, so we don't need to change the hollow cathode lamps, okay? So we can see all that summarized in the table on the right-hand side, and so a practical summary here is, for any multi-element or refractory element analysis, ICP-OES is the method of choice. FAS remains valuable for routine single-element QC at low capital cost. So if you've got a consistent thing that you need to measure, like for example, your process is running for 30, 40 years, and you need, the only thing you have to monitor perhaps is the copper effluent coming from your wastewater, then there's no real need for an ICP-OES. And a fast instrument would be perfectly fine for that. ICP-OES comes into its own whenever you're doing multi-element analysis. Perhaps you're an environmental analytical consultant lab or something like that. So how does it work and what are the advantages? And so one of the advantages is the heating source, the plasma source. But what is a plasma? So a plasma is a partially or fully ionized gas. So these are systems where electrons, ions, and neutral atoms coexist. It's the fourth state of matter, which is electrically conductive because, of course, those free electrons and ions are present. And so the ICP plasma is an atmospheric pressure argon plasma sustained by radio frequency electromagnetic fields. So the temperature range is about 6,000 Kelvin to 10,000 Kelvin in the induction zone. And argon is used because it is chemically inert and has a high first ionization energy and is commercially available in high purity. Okay, so the plasma initiation, how does that work? So the argon flows established through the three-tube torch. A Tesla spark is applied to the torch exit, which causes an ionization, which is a seed population of argon atoms. And so the initial electrons accelerated by the radio frequency field collide with further argon atoms, causing a pending ionization cascade. And so the runaway ionization produces the plasma within milliseconds, self-sustaining as long as the radio frequency power is applied, so 700 to 1500 watts. Okay, so this is a schematic on the right-hand side of sort of like how the heating works. And then, so why do we use argon? So argon, high ionization energy means it does not ionize so easily that the plasma runs away, nor so reluctantly that it fails to sustain. It is an ideal resistive medium for controlled radio frequency heating. So this creates what's called a skin effect. So this is why the plasma is toroidal. So at radio frequencies of 27 to 40 megahertz, the eddy currents induced in a conductor are confined to a thin surface layer, i.e. the skin in the plasma. This means the radio frequency energy is deposited in the outer annular zone, not the center. So the outer zone reaches 8,000 to 10,000 Kelvin, and the central channel stays cooler at 4,000 to 6,000 Kelvin. And so the sample aerosol will then travel up the cooler central channel, gradually heated from the outside in. And so the analytical consequence is that the sample does not travel through the hottest zone, and this hopefully prevents premature ionization before full atomization. And so it's controlled, it's staged heating. We have desolvation followed by vaporization, followed by atomization, followed by excitation in that sequence. And so this enables both the OES, the measure emitted light in the hot zone, and ICP-OES, which is extracting ions from the plasma tail. Okay. So the ICP torch gas flows and the viewing geometry. So the viewing geometry actually changes quite a lot here. So do we look at it radially or do we look at it axially? So do we look at end on, i.e. from above, or do we look at it on the side? So we have to consider that, generally speaking, which is going to be better for our system. So there are, of course, three different places that we can look at. There's the three concentric argon flows. There's the outer coolant argon, which flows tangentially, which cools the quartz torch walls and sustains the plasma outer boundary. Then we have the intermediate range, which has a slower flow and lifts the plasma off the injector tip and is used during ignition and positions the plasma vertically. And then we have the inner injector argon, which carries the nebulized sample aerosol through the central channel into the plasma. Okay, so this is where we have to decide on viewing geometry. So we have radial or axial. So the radial viewing, the optics collect light from the plasma side, which has lower sensitivity but has a wider linear range and fewer matrix effects, which is preferred for high concentration outlets. The alternative option is axial or end-on viewing. And so these optics look along the plasma axis. So this is 5 to 10 times higher sensitivity since there's a longer emission path to the viewing. And so it's more, but it is, however, more susceptible to matrix effects, but it is preferred for trace elements. Okay, and this is because of its higher sensitivity. There are some systems which can look at them simultaneously, and there are some which can switch between these two viewing points. So in order to do that, modern ICP-OES instruments use what's called an Echelle grating plus a cross-dispersing prism to project a 2D spectrum onto a CCD array, which provides simultaneous coverage of the full UV-vis range, replacing bulky polychromator PMT arrays. So a CCD is a very small, flat, almost like a flat screen TV type situation. So let's go through the sample's movement in ICP plasma. So the sample is injected from the spray chamber where the solvent evaporates partially, and so we only end up with small fine droplets entering the plasma. Then it enters preheating zone, which is above the torch, and the remaining solvent fully evaporates. The salt crystallizes, salt crystallites form. Then after that, we have the desolvation and the vaporization zone, which is where the crystallites vaporize and the molecular bonds begin to break. Then we move into the atomization zone, which is where all molecular species decompose to the free atoms, which is even true for refractory oxides. So this is your aluminum oxides, your titanium dioxides, which dissociate at these temperatures. Then we have excitation and ionization zone here, where the electron collisions promote atoms to excited states and they emit characteristic radiation of the excitation, which results in partial ionization. So this is why the refractory elements work in ICP. So aluminum oxide requires greater than 4,000 Kelvin to dissociate. The ICP atomization zone easily exceeds this at 7,000 Kelvin. And so in a 2,900 Kelvin N2O acetylene flame, dissociation is incomplete, and as a result, sensitivity is reduced. This, however, causes an issue with the need to be careful with our wavelength selection and background correction in ICP-OES. So we have to choose the analytical lines carefully. So the sensitivity here is that we select the highest intensity line, which is usually the tabulated recommended line. Okay, so we have this results in us having some relative freedom from the spectral overlap, and so we can check for nearby lines of major matrix elements using spectral databases. We have a linear dynamic range for shorter wavelength lines. They often have wider linear ranges. So this avoids the self-absorption at high concentration. And we have background problems as well, which is generally trying to avoid regions with high plasma continuum or molecular bands. We also have to worry about off-peak background subtraction. So we want to measure the background at 1 or 2 wavelengths adjacent to the analyte peak. So this is the off-peak positions. We want to subtract the interpolated background from peak intensity. And then we look at the idea that modern CC instruments are automated and they have manual selection of off-peak positions required for these complex matrices. So what is the linear dynamic range of an ICP-OES system? We have to understand the physical basis and the practical implications, okay? So in terms of AAS, we have like 2 decades to 3 decades of limited linearity. ICP-OES looks at, up to 5 or 6 decades, which is a significant sort of going from nanograms up to grams. Why does AAS, though, have this narrow linear range? So at high concentration, a dense cloud of atoms forms. So this results in self-absorption. So for example, the HCl emission line is reabsorbed by atoms between the flame and the monochromator, which reduces the IO. The apparent absorbance is then lower than expected. Ionization also increases, so this is reducing the neutral atom population. We have line broadening, which is Doppler pressure broadening to high atom concentration, which widens the absorption profile. And so the narrow HCl line now covers a smaller fraction of the profile. Then we have sensitivity loss. And so the result here is the calibration curve rolls over and curves downwards at high concentration. So why ICP-OES then has a wider range, 5 or 6 decades. So there's an emission mode, so no IO to self-absorb. The plasma is the source, and only the emission signal is measured. And self-absorption does eventually occur at very high concentration. So hot atoms absorb cooler atoms emission at the plasma edge, but this only occurs at milligrams per liter or gram per liter, and not at the micrograms, as in AAS. So ICP-OES can measure lead at 0.001 milligrams per liter and zinc at 500 milligrams per liter in the same run, same dilution. With atomic absorption spectroscopy, each element needs its own concentration range and often separate dilutions, which of course adds time to the analysis. Okay. So let's look at our worked example number 3, which is the internal standard correction in ICP-OES. Okay, so manganese is determined in river sediment digest by ICP-OES at 257.610 nanometers, with Y as internal standard, 371.029 nanometers at 1 milligram per liter concentration. So here we have our blanks, we have our standards, and we have our sample unknown. So we want to note that the intensity of Y drops 3.5% in the sample. This is due to matrix suppression. So the solution in the first step here is to determine the ratio of IMN over IY for each point. And then we can get the calibration slope as R versus the concentration of manganese. So we see that as here. So the ratio, the calibration is 1.122 milligrams per liter. Then we have a sample ratio then is going to be the 43221 divided by the 49200 from the table, and then we have the corrected concentration as being seen there. And so with the internal standard, we see that we have a minus 3.5% error. With the internal standard, the error is less than 0.3%. So this error is captured and corrected for. Working example number 4, so multi-element ICP-OES. So for example, looking at geothermal brine. So this is an industrial context problem. So geothermal brine from a power plant in Southern Leyte is analyzed by ICP-OES on the axial view for DENR environmental discharge compliance. So the sample is diluted at a 1:100 ratio, 1% nitric acid before measurement, and the reported concentrations are back calculated to the original brine. Okay, so we have all of the elements present there. We have their individual resonance lines, which are present as well. We have the concentrations and we have the limits of detection. And we look at the limits, D and R limits, and we look at their status. And we see that, for example, arsenic and boron are way over. So the analysis and decision, so arsenic and boron far exceed D and R limits. So the treatment is mandatory before discharge. Lithium and silicon have no discharge limit, but silicon is commercially recoverable as a silicon product. So it's actually high concentrations. You might actually want to get it because you can sell it. So why is ICP-OES essential here? So the concentrations span a very large linear range from 0.18 to 882 milligrams per liter. So that's a 4,000 times range. So the ICP-OES is 5 to 6 decade linear dynamic range, measures all of these elements in one dilution. FFAS would not be able to do this, and we would have to do multiple dilutions, and we cannot even measure the silicon or boron. So the real cost at 150 samples per environmental monitoring campaign, ICP-OES outcompetes the 6-elemental panel in one run. FFAS, which is only 4 measurable elements, would require 4 separate instrument runs. So we just have 4 times the time, reagent, analyst effort. In fact, it might even be more than 4 times that for the analyst effort because of the different dilutions required. So if we look at the complete technique comparison of AAS versus ICP-OES versus ICP-MS, which is an allied technique, we can see them here. We can see the different limits of detection, the numbers of elements which can be run individually. The decades of linear range, of course, are the best in terms of the ICP. We are good at dealing with refractory elements with ICP, but not with FFAS and GFAS. We have the sample volumes changing. We have the isotope information, ICP-MS only. Capital costs are very high, though, for ICP instruments. So, but they do have also higher throughput. So if you've got a lot of samples to measure, can be useful. Okay. So these techniques, increasingly, we're seeing the different environmental agencies prioritizing ICP-OES versus FFAS and GFAS, simply because they're more available now in the country, and also you're seeing that these techniques can analyze elements that are otherwise not analyzable using the F or GFAS. Okay. So in summary, we've covered these different techniques. Next time we'll look at interferences, quality control, and some industrial case studies. So as always, there are some practice problems. I encourage you to have a go at these. The solutions will be posted in Canvas, but make sure to attempt them first, and then we'll move on to lecture. But thank you for listening.